Well, this is the first video for Math 112 trigonometry. And as I was looking at this first assignment and thinking about talking about, what trigonometry is and how it's used and everything, this first assignment and those ideas are actually very closely tied to each other, because section 1.1 is all about measuring angles. And so what does that mean? Why do we do it? So an angle, is sort of the distance between two planes or lines or anything else. Okay? So this distance that is opening up here between my hands, this is the angle. All right? We typically draw it on the board, right, like this, to represent that opening. Okay? An example that I was going to use to show you is something like this. So right now, my arm is at about a 90-degree angle to the side of my body, and now it's at a different angle. Okay? And that's actually one place where people use angles is in physical therapy and in range of motion questions. Historically, the use of trigonometry goes back into fairly ancient times. A lot of it had to do with the sky, the night sky, astronomy and astrology. Both made a lot of use of keeping track of where the planets and the stars are in the sky, and that has a lot to do with angles and distances to some extent, but mostly the angles that those stars are, just to represent the positions of the heavenly bodies. And that, of course, leads to calendar making, because once you can keep track of the positions of the stars and planets, then you can keep track of time, and that's something that was done throughout the ancient world, was to make calendars based on the movements of the stars in the sky. And a lot of cultures, many of them in Asia, still have these astrologically based calendars. Let's see, what else? Navigation. Navigation makes extensive use of trigonometry in terms of angles and distances, as well as surveying and so on. Let's see. I'm trying to think if I left out anything important. There are a lot of important uses of trigonometry. Let's just go ahead and get started talking about how to measure angles. This section 1.1, we talk about two major ideas. One is what's called DMS notation, and this stands for degrees, minutes, and seconds. Okay, and that's how degree measure for an angle is often broken down. So this concept of minutes and seconds, well, let's first talk about degrees. So the degrees of an angle are defined on the idea that a circle, a complete circle, right, if you take this line and rotate it all the way around, that is the definition of 360 degrees, right? So that if you only go halfway, then that would be 180 degrees, and 1/4 of the way is 90 degrees, and so on. Okay. Okay, and this comes to us really from Mesopotamia, ancient, what's present-day Iraq, the Tigris and Euphrates rivers there, Babylon and Mesopotamia, use this idea of 360 degrees, and the minutes and seconds where, let's see here, degrees, we use the degree symbol, minutes is a single tick mark, and seconds is a double tick mark, and we get 60 seconds, just like in measuring time, equals 1 minute, and then 60 minutes, instead of equaling 1 hour, equals 1 degree. And those 60s also come to us from Mesopotamia. Their number system, we have a base 10 number system, so our place values are powers of 10. The Babylonians had a base 60 number system, and their place values were in powers of 60. And so that's where those units come to us from. Okay, so that's the DMS measurement system, and we'll go in the assignment. We'll go back and forth between decimal degrees and DMS notation. And then the other type of units for measuring angles are radians. And radians are defined, well, let's go ahead and talk about this. Radians, one of the key definitions here is that a complete circle is equivalent to 2 pi radians. So in the textbook I talked a little bit more about the formal definition of radians, how it is the angle, the number of radians in an angle is defined by the length of the arc of the circle that is outlined by the angle, the ratio of that length to the radius. So if you have a radius of 1, then it's just the length of that arc of the circle. Okay? And as a result of that, well, I'll go ahead and make a radius of 1. Let's say this radius was 1. Then the circumference of the circle, right, is 2 pi r. If the r is 1, then that circumference is 2 pi, and that's where that definition of the complete circle being 2 pi radians comes from. And so we've got this fundamental equivalence that 2 pi radians is 360 degrees, or pi radians is 180 degrees. And so we'll use that frequently to convert back and forth between degrees and radians. And all these different units, are used by different people in different situations. In calculus, it's actually very important to use radians rather than degrees, because radians have this basis in geometry that degrees really don't. And when you start having these degrees interact with other numbers in a problem, it becomes it just messes everything up. I don't know of a better way to say that. Whereas because of the basis of the definition for a radian, those things can be multiplied by other numbers with no problem, and they generate useful answers. Okay, so that's the basic ideas for section 1.1. Let's go over some problems. These are on, I think, pages 11 and 12 in the textbook, so let's take a look at that. Yeah. And the assignment looks like it's a lot of problems. If you look at it on the My Open Math website, it says problems 1 through 47, but these problems are very, very short and relatively straightforward. Okay, so these are on pages 11 and 12. I'll go through here and do the even problems, some of the even problems as examples, and then the assignment will just be the odd problems. Okay, so in problem 2, we want to take the angle 38 degrees and 20 minutes, and we want to convert this into decimal degrees, 38 point something. Okay, well, we know that 60 minutes equals 1 degree. Okay, so if we have 20 out of those 60 minutes, then that's going to be a fractional part of a degree. So that's what we want to do. We want to take the number of minutes and divide it by 60 to find out what that fraction is. This turns out to be 1/3, which is 0.3 repeating. So we write this as 38.3 with the bar over it to indicate the repeating degrees. Okay? I don't take a lot of points off if you leave the bar off, but I do take some points off. You know, that's the difference between, you know, 100% and 95% if you're taking a test or something. It's, you know, it's not a major mistake, but it demonstrates to me that you don't either really care enough to put the bar over it, or you don't really understand that it does belong there. Okay? If you've got a repeating decimal, use the bar. If you don't, it's not the end of the world, but I do take points off for that frequently. All right, let's see here. So that's problem 2, 38.3 repeating degrees. Let's see here. Problem 4 is similar. This one is 34 degrees, 10 minutes. We do the 10 divided by 60. That's 1/6, which is 0.16 repeating. And so our answer here is 34.16 repeating degrees. Okay. Let's see here. Problem 6. 165 degrees and 48 minutes. Let's see, if we do that 48 over 60, I think that should be 4/5. Yeah, so take that 48, divide it by 60. If you do it on a calculator, you just get 0.8 straight away without having to worry about reducing the fraction. So this is going to be 165.8 degrees. Let's see what else we've got here. Let's see, problem 8. 63 degrees and 35 minutes. So 35 over 60 looks like 7/12, and so that's going to be a repeating decimal, 583 repeating, with just the bar over the 3. And so this is 63.583 repeating degrees. All right, what else? Problem 10. Now we've got minutes and seconds in here. 141 degrees, 6 minutes, 9 seconds. Okay, so what we want to do here is we first want to convert the seconds into minutes. So we do 9 over 60, which is 3 over 20, should be 0.15, right? 9 divided by 60.15. So that means that this is 141 degrees and 6.15 minutes. Okay. All right. Now we're going to take that 6.15 and divide that by 60. Let's see what we get here. 0.1025. Okay. So that means this is 141.1025 degrees, and we can just leave it like that. As we're going through this, I've noticed that students sometimes have a habit of rounding off or just dropping digits that they don't want there. Like a lot of times people would just say, oh, this is just 141.1 degrees. Okay, if I ask you to round it to the nearest tenth, then that would be perfectly acceptable. If I don't ask you to round it, then don't round it. Okay, and this is frequently an issue in trigonometry because when we start talking about sines and cosines, you know, how many digits of accuracy do we really need? So the calculator will return answers for sines and cosines with like 8 digits of accuracy. something along those lines. So we don't need quite that many. On the other hand, if you only take the first 1 or 2 digits after the decimal point, you're doing way too much rounding and your answer will lose a lot of accuracy. I'll talk about this more when we get into this. A favorite example of mine is the GPS satellites. When they were first being put up and being used, I think this was back in the 90s, one of the satellites had been programmed with an error in the 10 millionths place. So let's see how many decimal places that is. Let's see here. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, the 10 millionths place. So that's the 7th decimal place. So you may think that that's not important, okay? That who needs that much accuracy? Well, I can tell you the GPS satellites need that much accuracy because an error in the 10 millionths place in the satellite results in an error of 50 miles on the ground. And 50 miles is a pretty big error. So that's just a way of saying I'm going to ask you to pay attention to how accurate your answers are and to be careful with your rounding. And fundamentally, if I don't ask you to round off, then don't round something off. There may be situations where I forget to ask you to round off and you do end up with a long, irrational number, okay? And that I'll just leave up to your judgment, okay? And that's the way I look at it when I'm grading something. If I make a mistake and don't ask people to round off something that turns out to be an irrational number, that's on me, and I'll give the grades accordingly. All right, let's see here. Let's take a look at problem 12. Here we've got 19 degrees, 12 minutes, 18 seconds. So again, the first thing we want to do here is to turn the seconds into fractional minutes. So we do 18 over 60. Let's see, that's I think 6 over 20 or 0.3. All right, because if we reduce that some more, that's 3 over 10. Yeah, okay. So this is 19 degrees, 12.3 minutes. So then we take our 12.3 and divide that by 60. And that's 0.205. So this would be 19.205 degrees. Okay. Now, let's see here. The next section, we've got degrees, decimal degrees that we want to change into minutes and seconds. And so in the first section, we were dividing by 60. In this next set, we're going to be multiplying by 60. Okay, problem 14. 159.84 degrees. So the idea here is that we want to take that point 84, multiply it by 60, and so this is 159 degrees, 50.4 minutes, and now ideally we want to take that point 4, multiply that by 60, and so this is 159 degrees, 50 minutes, and 24 seconds. And there we go. Okay. If we come out with a decimal number of degrees, there are no smaller units there that I know of, and so we just leave it. We would just leave it like that. We'll see if we have any problems in this section where we have to worry about that. Let's see. Problem 16. 24.56 degrees. Okay, so again, take that point 56, I'll write it down this time, take that point 56 and multiply it by 60, and that's going to be 33.6. So this will be 24 degrees, 33.6 minutes. Then take that 0.6, multiply it by 60, I believe that should give us 36. Yeah. So this is 24 36 seconds. Okay. Let's see here. Number 1864.16 degrees. Same process. 0.16 times 60. That's going to give us 9.6, so it'll be 64 degrees, 9.6 minutes. Then we take that 0.6, multiply it by 60, and just like we got over here, that'll be 36. So 64 degrees, 9 minutes, 36 seconds. Okay, let's see, we'll look at one or two more of these. Let's see here, problem 22. We've got 55.17 degrees. So we'll do the same process here. Take that 0.17, multiply it by 60, and what do we get? 10.2. So 55 degrees, 10.2 minutes, and then take that 0.2, multiply it by 60, and that'll give us 12. So 55 degrees, 10 minutes, 12 seconds. Okay, well I think that's good enough for this section. Now let's move on and look at radians and degrees. So the fundamental conversion for these problems is going to be that pi radians. So radians, there's no symbol for that unit, okay? So if you see an angle that's expressed in units that don't have a symbol along with it, then we can assume that they are radians. Typically, if there's any confusion, we would write radians to try to eliminate that confusion. So pi radians is going to equal 180 degrees. And that's our fundamental conversion. Okay, let's see here. So we want to convert these angle measures from degrees into radians. Well, I'm not going to make you memorize this, but I do want to talk about it briefly because I think that it's helpful. Okay, so pi radians is 180 degrees. That means pi over 2 radians is going to be 90 degrees. 180 divided by 2. Okay, what else? Pi over 4 radians is going to be 45 degrees. Let's see here. Pi over 3 radians is going to be 60 degrees. And pi over 6 radians is going to be 30 degrees. Okay, so those are some fundamental equivalences, and these are important angles. 90 degrees is a perpendicular, and that's been important to builders for thousands of years. Okay, and then if you split that in half, that's where our concept of 45 degrees or pi over 4 comes from. And if you split it into thirds, that gives us 30 and 60 degrees as well. Okay? So these angles, and also the 30 and 60, the 60 degrees in particular comes from the equilateral triangle, right? If we have an equilateral triangle, then all of these angles are 60 degrees. In radians, that would be pi over 3. Okay, so that is one way to think about these angles. And all I did to generate these was take 180 and divide it by 3. Take 180 and divide it by 2, and that's how I got these degree measures. Okay, you can always set up a proportion to do this, and maybe I'll do that with a couple of these problems. Okay, let's see what we've got here. Problem 26, we want to convert 120 degrees. 26, we want to convert 120 degrees into radians. So I'll think about doing this in two different ways. One way is to notice that 120 is 2 times 60. Therefore, that's 2 times pi over 3, or 2 pi over 3. Now, if you want to call this 0.6 repeating times pi, that's fine. Okay? Mostly in trigonometry, what you see is people using fractions rather than decimals. If you have a real aversion to fractions, this is still correct. I won't mark it wrong, but if you leave the bar off the 6, then it is wrong. Okay? And also, I think that it's good to be able to work with different ways of expressing numbers, okay? So if you have a fear of fractions, I would encourage you to try to get over it, okay? All right, let's see what else we've got here. Oh, another way to do this problem is to, well, in the textbook, I talk about this method for converting from degrees into radians, is to multiply the degrees, which are 120, multiply that by pi over 180, and you can see the 120 over 180 reduces to 2/3, and there's our 2 pi over 3. The other thing you can do is, if you're really stuck, you can always fall back on a proportion. You can say pi radians is to 180 degrees as x radians is to 120 degrees. Cross multiply and solve for x, and you'll find as a decimal that'll be 0.6 repeating, or 2 pi over 3. Okay, so some combination of any one of these 3 different methods is a good way to approach these problems. Whichever one, kind of makes sense to you, then I think that's the best way for you to do the problem. When I was in high school, I had to memorize these, and so they're stuck in my mind, and so it's really easy for me to do it this way, which I mentioned. If I see the 120 is 2 times 60, that's going to be 2 times pi over 3. Okay? And that, to me, is a good way to do these problems. You can use that pi over 180 multiplied by 120. You can also set up a proportion. All right, let's see what else we've got here. Problem 28. Problem 28, 225 degrees. Let's see here. What do we want to do? Again, I recognize this as being a multiple of 45. I understand that's not something that's going to jump into other people's minds if they haven't worked with trigonometry for many years and memorized that 45 degrees is pi over 4. So what do we do in the absence of that? Well, you can always... the fundamental idea here is 225 times pi over 180. And so what I'm going to do is I'm going to use the calculator. We could do it without the calculator, but you can always use the calculator to reduce a fraction. So if we take 225 over 180, 225 divided by 180, and then in the math key, first choice is turn this into a fraction. If it's already a fraction, it'll make it a fraction in the lowest terms, 5 over 4. So, we'll put our pi up there, 5 pi over 4, and you can see that's actually 5 times 45 degrees. And if you do 5 times 45, you'll see it is 225. So, 225 degrees is 5 pi over 4. All right. See what else we've got here. 150 degrees, problem 30. 150 degrees. That's 5 times 30. This is going to be 5 pi over 6. 5 times 30 degrees. 5 times pi over 6. 5 pi over 6. And you can also do the same thing that we did for this problem. you can take the 150 over 180, and you can use the calculator, or you can reduce it yourself and see that this is 5/6, and so this will turn out to be 5 pi over 6. Okay, let's see here. What else? Well, let's look at problem 34. 36 degrees. So with the calculator, I think it's helpful to leave the pi out, because if you put pi into the calculator, it's going to calculate it, and it won't just express it as a multiple of pi. So that's why I did this without pi, and then I put it back in at the end. I'll do the same thing here. Do 36 over 180, and then we can reduce it. And you can reduce this yourself, or you can use the calculator, however you want to go about it. But this is 1/5, and so therefore 36 degrees is going to give us pi over 5 radians. And you'll see, if you do 180 divided by 5, that should give you 36. All right, let's look at one more. Problem 36 is 104 degrees. And so let's do the same thing. 104 over 180. And let's see what we get here. 26 over 45. Nothing very exciting. So this is 26 pi over 45 radians. At that point, expressing it as a multiple of pi is not really that big a deal. We could just multiply this times pi and get some approximate decimal representation in radians for that angle. Okay, now the next set, this is the last set of problems here on page 12. These go from radians to degrees. So, well, problem 38 is pi over 5. I just erased that over here. That's going to give us 36 degrees. But let's go ahead and talk about it. So one way you can do this is you can multiply this by 180 over pi. The pi's cancel out. 5 goes into 180 36 times, so this is 36 degrees. Another way of going about this is just take the pi over 5, replace the pi with 180 degrees, because that's what it's equivalent to, and that just takes you to the same place, 36 degrees. All right, problem 40, pi over 6. There it is right there. Pi over 6 is 30 degrees. And again, you can just do 180 degrees divided by 6, gives us the same thing. Problem 42, this one's a little bit more interesting. 7 pi over 3. Let's talk about a couple different ways to approach this. So, again, what I've been talking about here is that you can go 7 times 180 degrees divided by 3. Okay, and then you can use the calculator on this if you want, but 3 goes into 180 60 times, and this is 420 degrees. Okay, you can also, so I was talking about how I had to memorize these, and so this is kind of stuck in my brain, so I always see this as 7 times pi over 3. And that's 7 times 60 degrees, which again is 420 degrees. All right, let's see here. 44 is actually very similar. This is 7 pi over 4 degrees. So you can go 7 times 180 over 4 and then calculate this in some way. Let's see, I think I will use the calculator here. The 4 is going to go into 180 and make it 45, but then we're still going to have to multiply 7 by that. So let's see here. 7 times 180, and then divide that by 4. This is 315 degrees. Or you can think of this as 7 times pi over 4, which is 7 times 45 degrees, which will give us the same thing, 315 degrees. All right, let's skip over to problem 48. Let's see what we've got. 7 pi over 2. So, again, you can go 7 times 180 over 2. That's going to be 7 times 90, or 630 degrees. Or you can think of it as 7 times pi over 2. 7 times 90 degrees. Again, 630 degrees. Okay, so that is the first assignment. That gets us started, at least trying to represent this idea of an angle. Okay, where is the, what is this distance in here? Okay, that's what an angle is all about. And its relationship, so that's the thing, is that these angles are fundamentally related to distances, is that you open an angle a certain distance, and then the length between those 2 points can be calculated based on this angle and the lengths of those 2 lines. That's the fundamental idea of trigonometry, is you can use it to measure things that you can't get to, okay? And so I've done this, with shingling. If you can't get up into the peak of a roof to measure it, but you can measure other pieces of it, then you can calculate something that you can't get at. And that is one big, major use of trigonometry. All right, so that's it for section 1.1. I'll post probably at least 2 more assignments for the first week, and they'll all have little quizzes that go along with them. And so that'll get us started in chapter 1. And if you have questions, I encourage you to contact me in some way. A lot of people do email me questions. I'm in my office pretty much every day. And so if I'm sitting there and you email me a question, I'll answer it. Okay? It's not the best. Sometimes we go back and forth trying to get things straight. But I haven't really had any situations where I wasn't able to help somebody understand what they had emailed me about. It's different from explaining something in person, but I've found that it is very helpful. Okay? You're also welcome to come visit my office on campus if the email is not helping you enough, because sometimes it's just you need to sit down with somebody and have a verbal back and forth, and that can be really helpful. Like I said, I'm in my office pretty much every day. Let me know you're going to come by. I'll make some time for you. So what I'm saying is, if you have questions, please ask. There's also the math lab is available. Celeste Peterson is running a math lab. It's most mornings from 8:30 to 1:30. So that information is on the syllabus. I'll try to communicate that in other ways as well. But if you have questions, please ask.